Hello, we're Team 13 presenting a DP3 report for our project, the Energy Elevator. I'm Jimmy Baldwin.
I'm Sam Melendez.
And I'm Andrew Sherman.
All right, so as we get into it, here's an overview of what we're covering. And we're covering our stuff pretty much based on how we did it in our DP3 report. For the sections that we filled out in the report we are presenting, it just makes the most sense that way. Here's our introduction. The goals for this project was to take a ball and perform a scientific task with it, which we ended up picking to be the conservation of energy, and then release the ball at the same speed that we were given it, so that in theory all of our projects could be lined up to be a Rube Goldberg machine. And the task completed since the last report, which was DP2, we finished the plan for manufacture, we finished the economic analysis, and we finished our prototype. Here's an overview of the project management, the Gantt chart. As you can see, everything is finished. In this case, we're wrapping up right now the present results as we do this video. And since our last report, we pretty much finished the bottom four things: plan for manufacture, economic analysis, prototyping, and present results, which we did on time. As you can see right here, just as the deadline, we finished everything. Here were the customer needs that we identified for the project. We interviewed potential customers, and what they came up with was that we would need a low-cost, safe for classroom environment, which was actually the most important thing, to be reliable, to be simple coding interface so that the students could use it easily, and that it would clearly demonstrate the concept so that there would be a reason for the purchase of the product.
So for the concept generation section, we first started out by identifying three subsets of our product. So three different sections of our product, which are right here. So entrance, is receiving, elevator, and exit ramp. We then came up with three different solutions for each subsection to create this concept combination table as shown here. From there, each person took a subsection to create possible solutions. And then we evaluated each of the solutions to find the best solution to make for the product. During the concept selection phase, we evaluated each solution first by identifying different target specifications from the customer needs, and then from there we went through the concept screening to find the solutions that had the most positive opportunities and advantages for each of the solutions. So the three solutions passed this concept screening, which were shown here as conveyor belt, elevator, and Hot Wheels solutions. We then did the concept scoring as shown here, and applied a weight to each of the selection criteria from that was identified through the customer needs. And then the one with the highest score was the product that we were going to create, which ended up being the elevator solution. The elevator solution turned out to be the easiest to build, very simple, and very clearly showed the conservation energy.
All right, and for our failure modes and effects analysis, we snipped out what we would call the text, which would say what would happen in each case, why it would occur, or why it would be so severe. But here are the numbers that make up the risk priority number. As you can see, the highest RPNs are going to be the guide ramps, which we initially did suspect that guide ramps would be the hardest thing to make line up, since they're taking the ball from the bucket and delivering it to the exit ramp. And to do that, we had to make several different adjustments on our prototype in order to get it to work correctly. The other thing that kind of surprised us was that the receiving bucket was actually pretty difficult to make, partially because of stringing it up and getting the ball to go into the cup and not bounce out or anything. It ended up being a difficult task for us. But overall, all of the different sections of the product will require some attention The least likely to give any trouble in the performance of the task would be the stand elevator, and the servo motor was pretty simple to code and pretty simple to use. It should be easy to detect any failures that might occur because the code would give you an error code before you even ran it, so you would know ahead of time if you had a failure in that instance.
So for the product architecture, our product has a modular architecture. There's each chunk only does one or two operations, and they're not very dependent on each other except for the one before it. So here are the four different chunks we have. So we have receiving, elevation, exit, and control interface with the Arduino. Because of the modular architecture, it would make it very easy to replace either one of these chunks with another design to create a new version of the product. For example, you could replace the elevation, which consists of the pulley, servo motor, and elevator stand, with a Ferris wheel type thing where it scoops up the ball and gets it to the right elevation. Or you can replace the exit with the exit funnel ramp idea with a spiral ramp that would gain speed as it would have the ball gain speed as it exits. And so then for the industrial design, we have, as shown here, we assessed the industrial design with all these assessment categories. We found that overall we met the industrial design goals. The only, I guess, low rating we had was the ease of maintenance, as that was not high priority in the beginning for the customers. Safety was the biggest thing. So we did not focus on making a product that would be easily repaired by replacing parts, excuse me. So hence the lower score, since it'd be very hard with everything that we have put together and strapped down to either take out and repair a part. So most likely it would have to be sent back and replaced with a full new product. Like I said before, the safety, highest priority, and we have the highest rating as we feel that is fully safe for a classroom environment. And the product's also unique, so that's a good enough product differentiation for the small market that we would be selling in. So we feel like we met that correctly well.
So this is the 3D CAD model of our final prototype for the energy elevator. You can see here we changed the colors to make it easier to distinguish what parts, one part from another. So in red here on the top we have the descending chutes that takes the ball from the pulley down to the ramp, which is red in the bottom. We have the cup elevator here, so the entrance ramp with the ping pong ball would be over here, and the cup receives the ping pong ball, where the Arduino in black here will power the pulley that pulls up the elevator, and the cup will get caught on this stand here, this peg. That's just to catch the ball, or the cup, so it doesn't fall and interfere with the ball on the way out. This ramp here is the part that is interchangeable between different sizes of this base here. This CAD model helped us fully build our prototype and visualize all the concepts and make sure that we have everything that the customer asked for. So building the prototype, we created a cost sheet of all of the materials that we used in the making of the prototype, but replaced some components, materials with what we would actually be manufacturing with. So whereas for the stand, it was mostly made out of cardboard for the prototype, we decided to change it to ABS plastic. And for the two stands, it would be roughly 1 kilogram of plastic. This is to give us a better understanding later for how much would go into manufacturing the product. So here is the full cost analysis. We had earlier that the for the cost sheet was about $43. Here, the cost of manufacturing is $44.44. This is in part to the labor costs. So how much the energy elevator would cost to manufacture in a factory, help pay the workers, and pay everything to make it. We did a quick markup to figure out the retail price, which we set at $79.99, which we then took those two numbers and calculated a projection of how much profit we would have at the end of year one. This is strictly for year one. By the end of it, we expect to build 800 units. Then we expanded on that year one projection and increased it by 400 units per year, and then took into account an investment proposal for VTEPs, for requesting how much money that VTEPs would be offering, willing to pay us to get this started. So we requested a lump sum of $100,000, and we plan to pay it back based on our profits of our certain quarters at the end of a 3-year time span. So for the changes that we would look in the future, we would like to make it a fully automated switch that controls the Arduino. So instead of what we currently have, where to unwind and wind the pulley, we have to upload 2 different codes. We would like to, in future developments, have a switch that one way goes up and one way goes down, to make it easier on the user. We would also like to find the coefficient of friction between the ping pong ball and the material that we are making in this, in the future case, ABS plastic. In our prototype, we had difficulties trying to figure out how high the ramp had to be that sends the ping pong ball to the exit ramp. We forgot to, at first, take friction into account, which takes away the ideal situation where a 3-inch ramp goes to a 3-inch ramp. It turned out being that to get up the 3-inch ramp, we needed a ramp height of 4.5 inches. So we would like to find the coefficient of friction. It gives the students a better understanding of reality versus the ideal classroom environment. And we would like to condense the code for an easier operation to make it, once again, make it as easy as possible for the user. We don't really want a complex code because some people may not have a background with Arduinos or coding in general. So overall, Team 13 went through the full design process, starting with just asking physics teachers and students what they would like to see in their classrooms and picking a topic, all the way to building the prototype and presenting it. Throughout the entire way, we kept a detailed economic analysis that focuses on how much we would have to pay to get this up and running, and how much we've got left. And overall, we think it was an overwhelming success.